Can somebody tell me the definition of a group? A set with a binary operation. And what properties does it have? Associative, identity, and this. Okay, so these three properties, that the operation is associative, then the identity exists, and the operation has an inverse, these three properties are known as axioms, or those three axioms together are known as the theory of groups. Okay, so what is a group? A group is a model of the theory of groups. Okay, a group is a model of the theory of groups. I mean, you might see it seems like I'm talking about something anticlimactic. I'm using the word group, but the theory comes first and then you label its model. In a similar fashion, the topic for our today's discussion is going to be model categories. So what are model categories? Now here actually the thing that it is model of is suppressed. So model categories are known as the categories of models of homotopy theory. Okay, so categories of models of homotopy theory. Okay, so far you have seen one kind of homotopy theory in our lectures. Do you remember what it was? Which category had a notion of homotopy? Chain maps. Yeah, the category of chain complexes had the notion of chain homotopy. Now this particular notion was actually borrowed from the concept of homotopy from algebraic topology. Yeah, I mean homotopy from topology. So topology and the category of chain complexes both have some appropriate notion of homotopy. Okay, but can we abstract these properties out? And can we do something like a generalized framework in which we can talk about homotopy? Well, first of all, when you think about homotopy, naturally, the first thing that comes into your mind is a disk being contracted into a single point. Yeah, it's a continuous deformation, like the shape essentially doesn't change. Yeah, disk is being contracted, so it's a contractible space. So this notion of continuous deformation, what does that mean? That we are taking this map from a disk, the constant map, to a point. Now that map we would like to say is invertible. Okay, so we would like to invert certain maps which we want to call as homotopy equivalences. We did the same thing while constructing a homotopy category of chain complexes. We inverted homotopy equivalences between chain complexes, and while constructing derived categories, what did we invert? We inverted quasi-isomorphisms, the morphisms which induce isomorphisms between homology objects. Okay, we did that. Now here also the purpose is exactly the same. We want to invert something, but whenever we invert something, then there are set theoretic issues. We discussed them last time also, a couple of times actually, when we defined the localization and when we discussed this roof and sink construction, because generally it's going to be a zigzag of morphisms. Now those zigzags, well, the middle object is actually taken from a proper class of objects. So therefore, in the new category thus formed, the morphisms between two fixed objects, those morphisms actually do not form a set, a small set. Those morphisms form large sets, or proper classes. So therefore, we do not like that type of construction. So model categories, on the other hand, they will tell us how to obtain this homotopy category very simply. Okay, we want to invert certain morphisms and we will do that. But it should be done in a very natural way, that the category should itself have enough structure that everything will be smooth. Okay, so the purpose here, so the purpose is, of course, localization. But remember, when we described multiplicative systems, we had abelian or additive categories at our disposal. So there was something extra present. Now model categories do not have any such structure, do not necessarily have such structure, okay? They might be like, maybe the category of sets itself can be thought of as a model category. I will describe what these things are, but the purpose is again going to be localize. Everything we want to localize. And from given a category C, given a model category C, once again, let me remind you, model category means the category of models of homotopy theory. Okay, given a model category C, we would like to define its homotopy category HOC satisfying the following. So HOC, the homotopy category of C, if you take any two objects, the objects are going to be the same as usual. We do not really change the objects, but they will be, they can be thought of as morphisms in the original category C itself from some functor applied on some two different functors applied on this. So XC is the so-called cofibrant replacement functor and YF is the fibrant replacement functor. And once we do this, then we will get, and this is the notion of homotopy. So homotopy equivalence classes of maps between two other objects. Yeah, that's how we are going to do this. Okay, now once we start talking about model categories, two important names have to be mentioned. The first one is obviously the person who introduced them. His name is Quillen. Yeah, Fields medalist who worked on K theory, and after winning Fields medal in 1967, he developed this notion of model categories. And another Fields medalist, Vygotsky, okay, so he also won Fields medal, and after that he became interested in this kind of setup. So in 1997, he worked a lot on simplicial sets, some model structure on the category of simplicial sets, which forms the basis of a modern branch of logic, computer science and philosophy or mathematics also, called the homotopy type theory. So model categories lie at the basis of something very fundamental. Yeah, homotopy type theory, or also Vygotsky's main contribution, you can say that he introduced model categories in algebraic geometry. When Quillen was doing this, then he introduced it from topological perspective, whereas Vygotsky did it for the purpose of doing algebraic geometry. Now there is a popular area of algebraic geometry called A1 homotopy theory. Yeah, that's all based around this. So Quillen and Vygotsky, two Fields medalists, thought that this area is important after they were well established names. So definitely it's worth looking at this interesting area, and it's a very abstract setup, but I will try to give you some ideas. We'll just have one lecture on this topic, not more, but I will try to give you as many ideas as possible. Well, before we go anywhere into the definition of a model category is pretty long, but before we go to the definition, I want to establish some kind of terminology. So, and this is coming from the category of chain complexes. Yeah, a chain complex is said to be exact if it is exact at every point. Yeah, it's a long exact sequence. Now, long exact sequences are also known as acyclic. Okay, so chain complexes are exact or equivalently acyclic if they are exact at each degree, exact in each degree also, that's correct. So acyclic chain complexes. Now normally when we want to describe some property of maps and property of objects, if you remember when we were talking about Serre subcategories, yeah, the class of morphisms with respect to which we wanted to localize the multiplicative system, it was generated by using those morphisms whose kernel and co-kernel lie in the Serre subcategory. So this is a kind of interplay which lies at the heart of anything that you do in category theory, that object to morphism, morphism to object. Yeah, so this interplay is very important, and now if you remember we described quasi-isomorphisms last time, the morphisms which induce isomorphisms between homology objects. Okay, so recall that, okay, just give me a moment. Okay, so recall that a quasi-isomorphism between chain complexes I mean, let's say f dot from a dot to b dot is a morphism such that Hn of f dot is equal to, is an isomorphism for each n in Z. So recall that this is a quasi-isomorphism. Now, can we check this on the basis of some object being exact? I mean, there are two motivating questions, like we want to test whether a given morphism is a quasi-isomorphism or not. And the second one is, does this f dot fit in a long exact sequence or a short exact sequence, whatever you want to call it. So the answer is yes. And what we do for that is construct the cone. Construct cone of f dot a chain complex whose, I mean, what is it supposed to do? It's supposed to mimic the construction of cone, mapping cone. This is called a mapping cone in topology. It's a chain complex with cone F nth entry, it is just going to be n minus 1 direct sum Bn. And if you have cone F n minus 1, then what will it be? A n minus 2 direct sum B n minus 1. Now I have to describe the the maps between this, the boundary maps. The boundary map is like this. Whatever is the boundary map here, I take minus of that. Whatever is the boundary map here, I just retain what the boundary is. And an minus 1 to bn minus 1, I take minus f. I'm not writing the indices, but the indices are clear. So this is supposed to mimic, you have to think hard for that, and I don't have enough time today to explain that. But it's supposed to mimic the construction of cone from topology. The mapping cone of f is, please look here. You generally, let's say, have a space here, x, and then you identify, you construct a cone over it. You know cone construction? You take the cylinder cross I and then you pinch the topmost copy. You construct the cone and then you identify this bottom copy of x with its image in y. So that is the pasting that you are doing. That is the mapping cone construction, and this is supposed to play the same role. Okay, and what is the role of mapping cone? That there is a short exact sequence. There is an SES, short exact sequence, like this: 0 to B dot to cone F dot to A minus 1, 0. Okay, so what is A minus 1? Like here I should write a note for that. So A P N is just A n plus P. Okay, that's the notation. So it is simply a translated copy of A itself. But there is a short exact sequence, and that allows you to embed all the homology groups of A dot and B dot in a long exact sequence. Yes, you remember that if there is a short exact sequence, then you can get a long exact sequence of homologies. That yields, a long exact sequence which is going to be like this. So dot 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 h n plus 1 cone f. Okay, then hn a dot, hn b dot, then hn cone f dot. So what is going to happen with this? When you compute the homology of the translated chain complex, then it will be the translated homology appropriately. Nothing will change. It's a local property anyway. And then hn minus 1 of a dot and so on and so forth. And the point that I was trying to make is, so this is the remark that f dot is a quasi-isomorphism if and only if cone of f dot is acyclic. So quasi-isomorphism testing can be done via acyclicity testing of some object. And this is an important point. And if homology, like quasi-isomorphisms, are your appropriate homotopy equivalences or the maps with respect to which you want to invert, then acyclicity is an important property. So therefore, we will also borrow this terminology in model categories. For describing homotopy equivalences or weak equivalences, we will also borrow this terminology. And while defining homotopy also, this kind of setup is useful to have some kind of mapping cone. There is a similar construction of a mapping cylinder as well. So mapping cone or mapping cylinder, they can be used to define two different versions of homotopy. Left homotopy, right homotopy, and in certain appropriate setting, the left and right versions will coincide to give you only one notion of homotopy. Okay, I'm pouring a lot of information, but that's my goal today. Yeah, I want to tell you lots of things. Okay, so now we are ready to start discussing the construction of the definition of a model category. Okay, a few things at the beginning, this will be important. So the category of arrows, I never mentioned this in my lectures so far because I did not want you to get confused with the arrow category. The category of arrows of C. C is a category, and what is the category of arrows? It is denoted C arrow, okay, and whose morphisms has arrows of C as objects and morphisms and commutative squares as morphisms. So what will be identity in this category? Simply speaking, so I have this map, yeah, this F and this is G. Then what is a morphism from F to G? It's a commutative square. Pair of identities will be the identity, and then composition will be stacking of such commutative squares. Yeah, so it's simple. Yeah, nothing hard happening here. Okay, so now we are talking about retracts. These are all topological concepts. Deformation retract, yeah, it's a continuous deformation. You can bring it down to the single point, and that single point embeds in the disk, let's say as the central point. And then that you call as a deformation retract, that one-sided thing, like the inclusion followed by surjection is identity, and everything is continuous. Okay, so retracts in C arrow, what is this? They are just, so F is a retract of G. If there is a diagram, if there is a commutative diagram, okay, so this is F, this is G, this is F, so there are some arrows here such that this composition is identity and this composition is identity. So that's exactly the same definition in topology. So F is a retract of G. Okay. Then another thing that we will need, like other two properties we will need. One is functorial factorization. Now this is a thing that is motivated by our standard image factorization. Huh? In the retracts what? No, I never said F and G are isomorphic. I just said F is a retract of G if there is a commutative diagram like this. No, I never said they are isomorphic. This outer arrow from F to F, that is identity. Huh? Yes, one-sided. So that's like both the map from F to G is split mono and map from G to F is split epi in the arrow category. In the category of arrows, not the arrow category, because arrow category is something different for us. Okay, so in category of sets, you can always factorize something. Given any function, you can factorize it as an epimorphism followed by an inclusion. Then in the category of abelian groups also you can factorize something, and that middle object can be determined uniquely up to isomorphism. So you can say that this particular map which takes F to its image and F to its co-image, these are functorial constructions. Okay, so that is what functorial factorization is trying to capture. So alpha, it is a pair alpha comma beta, where alpha and beta are functors from the category of arrows to itself, such that for any F in C arrow, F is equal to beta F composed with alpha F. Okay, we just gave it some name, and whatever we have seen so far, those image factorizations, they were all functorial factorization. So these are still some simple enough properties, and then finally we need to talk about lifting properties. Okay, so say that a morphism I has the left lifting property with respect to P, or a morphism equivalently P has the right lifting property with respect to I. If whenever you draw this I and P and you have a morphism between those two, so this is for all, there exists a diagonal filler such that both the triangles commute. Okay, I am not even writing objects now, you can understand what I am saying. So whenever we are given an inclusion, like I is supposed to be thought of as an inclusion and P is supposed to be thought of as a surjection, projection. Yeah, so inclusion, projection, and then there is a lifting property. You can actually check this in the category of sets. Yeah, that every inclusion has the left lifting property with respect to every surjection. Okay, understood this part? Yeah, so let me write that as an example. In sets, monos and epis. Yeah, so enjoy lifting properties with respect to each other. Actually, it is both ways. So if I is a mono and P is an epi, then this will always hold. And if some morphism I has the left lifting property with respect to all epimorphisms, then it is necessarily a mono. And if some morphism has the right lifting property with respect to every monomorphism, then it has to be an AP. Moreover, the roles of mono and AP can also be swapped. Okay, so there are lots of things that you can play around with. So these are the lifting properties, and if this diagonal filler is unique, then we say that I and P are orthogonal to each other. Okay, so I'm not writing the notation because, as usual, I do not remember what I should, which one should be on the left and which one should be on the right. Yeah, so therefore, I'm not writing the notation. So this lifting property is really important. Okay, so from this actually we can describe what we call a weak, yes.
If the diagonal is unique for I with respect to P, then will the other way around be true?
No. No, it has to have some sense of direction, but I'm not writing it because I don't remember the convention. So either you will say that I is perpendicular to P or P is perpendicular to I, but not both. Weak factorization system. Okay, so this means it is a pair of subcategories EM. Yeah, weak factorization system like AP mono, you can continue thinking about them as this, such that first property is that each E in E has the left lifting property LLP with respect to each M in M. Then second thing, subcategories I should say of C, okay, C is the category that is given. If F in morphisms of C has the left lifting property with respect to each M in M, then F actually belongs to E and their duals, yeah, and 1-op and 2-op. 2-op you understand, like 1-op means that each morphism in M has the right lifting property with respect to each morphism in E, and whenever a morphism has the right lifting property with respect to each morphism in E, then it belongs to M. And lastly, yeah, I mean this is 1-op, 2-op, and third condition is that if F belongs to more C, then there is a factorization like this. So this is an E and this is an M. That is functorial. Okay, so this functorial factorization is being encoded in this. Maybe I should write WFS over here. No, I mean E is a collection of morphisms. Yeah, so morphisms which are closed under compositions. So that's why I'm calling it a subcategory. And which also contain identities. Yeah, that's. Huh? No, each E in E. Okay. Here I am using an abuse of notation where I am referring to a collection of morphisms containing identities as a subcategory. It's not a full subcategory. Normally, when we talk about a full subcategory, we only talk about the collection of objects. Here I am talking about only morphisms. So whenever these morphisms are present and they are closed under compositions, then their domains and codomains are also present. Okay, so simple such things. Okay, so this is a weak factorization system, and mono-epi and epi-mono are both weak factorization systems on the category of sets. You can verify that. Yeah, I will leave it as an exercise. But now, like we have got enough of setup to start talking about the model category. Okay, so given a category C, a model structure on C is a triple of subcategories satisfying the following. I'm writing a long definition here. Some of these axioms can be derived from others, but I will anyway write all of them. Okay, so I'm going to mention lots of axioms, yeah, just to be more explicit. Yeah. You need lot of data. Yeah, this COF is called cofibrations, W is called weak equivalences, and fib is called fibrations. Okay, so COF is supposed to be nice inclusions. Fib is supposed to be, the fibrations are meant to be nice surjections, and W is weak equivalences, so they are supposed to capture the notion of homotopy equivalence. Cofibrations, fibrations, and weak equivalences. Okay, so these three categories we need. So the first property that we need is 2 out of 3. For W. We have discussed this once, 2 out of 3. So if FG are morphisms in C, such that G composed with F exists in C, and any two of F, G and G composed with F are weak equivalences, then so is the third. So basically what we are saying, one thing is clear, yeah, if F and G are weak equivalences, then G composed with F is also a weak equivalence. That's clear? because it's a subcategory. W is a subcategory. Yeah, so the other two, however, they are important. But the short form is 2 out of 3. If 2 out of 3, then all 3. Okay. The second condition, yeah, that all cough, W and fib are closed under retracts. We have already discussed retracts, so these are all subcategories closed under retracts. Yeah, no harm in assuming this condition. The third and third op, they are interesting. Yeah, so cough intersection W, comma fib is a weak factorization system. And the other thing, like I'm just calling it 3-op, although it's similar. So cough, comma, fib intersection W is a weak factorization system. And let me write some names for you. So I haven't written names. So these are called acyclic cofibrations. And these are acyclic fibrations. These are just fibrations and these are just cofibrations. So we have got two different weak factorization systems at the same time. And if you look at this data, then this data is symmetric. You can simply take the opposite category C-op and the opposite morphisms of cough will become fib-op, like in the dual category. Then opposite of fib will become cough and W will remain as it is. The roles will be reversed. So if C has a model structure, then so does C-op. Yeah, I already described what it is. So remark, if C has a model structure, then so does C-op. The roles of fibrations and cofibrations will get reversed. However, you can see that the definition itself has some sense of direction, because in weak factorization systems, left lifting property and right lifting property, yeah, that's a distinction. So left lifting property, the morphism always has to be a cofibration and the right lifting property always has to be a fibration, whether it is acyclic or not, and one of them will be acyclic. Then it will have this diagonal filler. So this is the definition of a model category. Sorry, model structure. I haven't yet defined a model category. So let me do that. It's just one line extra, that a model category C is a complete co-complete category C with a model structure. Okay, so we are just adding that all limits and co-limits are present. Originally, Quillen just wanted finite limits and finite co-limits. But over a period of about 50 to 60 years, that definition hasn't really proven to be useful. in all the examples that you consider, they are complete and they have all small limits and all small co-limits. So therefore that hasn't been interesting. Another piece of notation that I should give you is there are two functorial factorization systems. Functorial factorizations. So the alpha, beta and gamma and delta, they correspond to these four classes. Yeah, if you ever see literature, then you will get these notations. So the data of model structure actually consists of three subcategories with two functorial factorizations, such that you list out all the properties of it being weak equivalent, weak factorization systems. Now, if you remember the definition of a weak factorization system, then if you are given E, then you can uniquely determine M, because M consists of precisely those morphisms which have the right lifting property with respect to all maps in E. You understand that? Yeah, it's a tight condition. Yeah, it's a tug of war. If you add more conditions on the others on one side, then the second side will, like if you add more morphisms in E, then there will be fewer morphisms in M. If you add more morphisms in M, then E will increase. So E and M are in a tight situation. So if M is determined entirely by E or vice versa, that E is determined by M. So if you look here in the definition, 3 and 3-op, if you only know cofibrations and weak equivalences, then you automatically know what fibrations are, and you also know what acyclic fibrations are. Yeah, because acyclic fibrations are precisely those which have the right lifting property with respect to all cofibrations, and fibrations are precisely those which have the right lifting property with respect to all acyclic cofibrations. So it is sufficient to give the data of only two subcategories, cofibrations and weak equivalences. But this kind of presentation is nice because it's symmetric. Yeah, it's balanced presentation. Cofibrations and fibrations and weak equivalences, trying to balance things out on both sides. Any questions so far?
So the model category need not be pointed.
Model category need not be pointed. No, I haven't assumed anything related to pointedness or any enrichment. It's plain bicomplete category with a model structure.
So you can say that the Waldhausen category actually sits inside this, because it's.
Well, let's not go there. Yeah. Model categories, Waldhausen categories only have cofibrations and weak equivalences. They don't have the concept of fibrations. They don't have the concept of fibrations as far as that.
So that's what I'm saying.
No, they have different properties. It's not the same setup.
So here the cofibration and weak equivalences do not have those properties that we have.
No. Waldhausen's construction is entirely different. The purpose is still the same, that you want to localize at weak equivalences, but this is a very different setup. By the way, the material that I am covering is mostly from Mark Hovey's book. Yeah, Mark Hovey wrote a book in late 1990s. It's available online for free. Okay, so I already mentioned that it is sufficient to describe only two classes, cofibrations and weak equivalences, or fibrations and weak equivalences. In practice, people prefer cofibrantly generated model structures, which means cofibrations are given, weak equivalences are given, and then you do not talk about fibrations, they are automatically there. I would like to give you some examples, but those are like highly trivial examples. I don't think you are ready yet to understand more complex examples. The first one is the trivial model structure on any category. So trivial model structure like COF, W and fib, I have to describe that, yeah. So COF is all, then this is ISO, and fib is also all. Okay, so very boring example that you want to invert isomorphisms. So you don't really do anything, you retain whatever you had. Okay, so nothing happens here. The second thing is, this will be a very weird statement to hear. Yeah, normally in category theory we do not really use numbers, do we? The abstract structure of numbers is not relevant, but here we are doing counting. So there are exactly 9 model structures on the category of sets. Okay, exactly 9 model structures, but they are all boring. Okay, they don't really give you anything. So for example, mono, all, epi, then epi, all, mono. So you want to invert everything, and then mono and epi, epi and mono, that doesn't matter. No, we just need a tuple, 3 tuple, right? 3 tuple of categories, subcategories. Co-fibrations, W, and like weak equivalences and fibrations. Huh? What is B? No, there is no fourth component. It's just a triple of subspaces. Yeah, fibrations, FIB. So there are exactly 9 model structures on the category of sets, and the proof is easy enough if you understand what's happening. You can argue. There's also some Mexican UNAM website. Somebody has done this proof nicely. You can check it online. The more interesting examples will of course come from the category of topological spaces, the category of simplicial sets, and the category of chain complexes. Okay, these 3 are important. There are also some model structures on the category of all small categories. Yeah, so the 2 category of small categories. Okay, but what do we use it for? We said that the purpose is to define localization, so let's define localization. And before we do that, of course, we can talk about something like this cofibrant replacement functor or replacement. This is a functorial construction. So we just said that if C is a model category, then it is complete and co-complete. In particular, it has an initial and a terminal object. Okay, so consider the alpha beta factorization of the unique arrow from 0 to x. Yeah, what will it look like? It will look like this. Zero to xc to x, and in order to denote that there is a weak equivalence happening, I am writing this tilde sign. So what I am saying that the map from 0 to xc is a cofibration, let me scroll it up a bit. Alpha is a cofibration and beta is an acyclic fibration. So this Xc is the middle object for this. So you have a functorial factorization. So X mapping to Xc, this is the cofibrant replacement functor. So X mapping to Xc is the cofibrant replacement functor. On the other hand, we can play the same game with the unique map from Y to 1 and we will get a fibrant replacement functor. Okay, so Y to YF is the fibrant replacement functor. And what's happening, like I take Y to 1 and then YF and the unique thing. And this is the weak equivalence. This is the gamma delta factorization. Yeah, the other weak factorization system we are using. So when do we say that a particular object is cofibrant? So say that X in object of C is cofibrant if 0 to X is a cofibration. The full subcategory of cofibrant objects is denoted CC. Okay, then fibrant objects, what we will say? CF. And cofibrant fibrant objects both is denoted by CCF. Any questions so far? Okay, so then you can obviously imagine that there will be inclusion functors. Cofibrant fibrant objects are obviously fibrant as well as cofibrant and they all include into this. So these are inclusions of categories. Okay, hopefully you understand all these things. So normally what happens now, the motivation comes from topology, so that's why I'm trying to resist talking too much about it. But there are some topological spaces which are nice, namely the CW complexes. CW complexes are those where you can identify some points and then you construct it by, like, if there are points then you can draw a line between them, then line you can, like if there are 2 lines, then 3 lines, then you can fill up something, or even between 2 lines you can fill up the area between them, right? Or and basically it has to do with the embedding of the boundary circle into the disk, and then you can fill that up as you please. And because of this constructive nature of all these topological spaces of CW complexes, CW means there is some countability condition as well. So these spaces can be built in a systematic manner. However, it's not necessary that the base point, the base of this construction has to be an empty space or a single point. What you can do is you can start with any topological space, and then on top of that you start adding some structure, like some cells. So for example, Cantor set is a bad topological space, right? It's a spectral space and it's uncountable and still has measure 0. Those properties you have seen, measure has nothing to do with its topology. But in Cantor space, if you want to construct, like if you want to build a CW complex out of the existing data of the Cantor set, like I connect 2 points by a line, and then I connect those 2 points by another line, then I fill up the area between them. Now I take some quotient topology, and then I fill up the space between them. So I can start anywhere, but my successive constructions are all CW constructions, like cell constructions. This is called a relative cell complex, the inclusion of our base space into this new space where the steps include just addition of cells and quotients. This is called a relative cell complex. So it means that the original thing could be bad, but their ratio, essentially the ratio or the difference between the source and the target, that is a nice space. Yeah, so the process by which you obtain this new space from the original one is important. Now such things or their retracts, they are actually the cofibrations in the standard model structure on the category of topological spaces. The relative cell complexes are the cofibrations. Okay, we are going to do it in a slightly different way, like more formal way, and then what will be the fibrations, what will be the weak equivalences? Well, there will be homotopy equivalences because that's what we want to do there. And once you know these two classes, then you can figure out the rest. However, like one more important feature is of this particular construction is that the cells can be described. Yeah, like you want to fill up some space. That is what a cell is. If I'm given the boundary of a circle, then I can fill up the interior. If I'm given the sphere, then I can fill up the interior, and so on and so forth. So there is only a countable collection of such morphisms, and these things can be obtained, like any relative cell complex can be obtained by taking, yeah, please pay attention, transfinite compositions of pushouts of these maps. Transfinite compositions of pushouts of the standard maps. So the relative cell complex construction is actually a pushout of the standard inclusion. At every step it is a pushout, and then we are doing it transfinitely. Okay, so these are too many things to say. I will write a few things down for you to understand. But ultimately, we want to capture the homotopy category, right? So let's look at this version of left homotopy and right homotopy for a bit, and then we'll come back to this. So cofibrant replacement functor, what will it do? Yeah, okay, I mean that's why I started with this whole discussion. So cofibrant replacement functor will take a topological space, and then it will only remember what maximal part of it was constructed as a cell, a CW complex. So it will replace every topological space with a CW complex or a version of it. I'm just being vague here. In such a way that the CW complex thus obtained, XC and X, they are homotopy equivalent. Okay, so that's why like it looks very abstract kind of setup, but it has got very deep rooted intuitions coming from topology. So let's do this interesting homotopy construction, the internal homotopy construction. So, okay, so given f and g from B to X, yeah, a cylinder object for B is any B prime such that there is a factorization like this. Okay, so B plus B, you understand B plus B? It's the co-product. Then from co-product to B, we have the map. What is the map? It's identity, comma identity. This map we always have. Okay, and finally we have this. This is I0, comma I1, and this is B prime, and this is a weak equivalence. Okay, so here what I need is that this is a cofibration. Let me just write cof, and this is a weak fibration or acyclic fibration. People also call it the trivial fibration. Okay, so there is a factorization like this. A cylinder object is something that lies in the middle. Now think about it topologically. What's happening? We are given two different copies of B. Yeah, this is a visual thing. Two different copies of B, and I have a map onto B. And B dash is just a cylinder. You embed these two disjoint copies into the cylinder. And B dash, which is just B cross I, yeah, in topological spaces. So B cross I to B, that is a homotopy equivalence. You all agree? Cylinder is homotopy equivalent to the original space. So that's precisely this cylinder object. The standard, yeah, the standard cylinder object is denoted B cross I. Okay, B cross I doesn't really mean anything. Please be aware, there is no product happening, but just we want to understand it in our normal terms. So therefore B cross I. And what do I mean by standard? Like functorial factorizations, yeah. So use functorial factorization. What I described was any factorization, right? Any factorization like this will give me a cylinder object, but if in particular I use the functorial factorization, and which one? Alpha beta. Then the middle object, which is unique up to isomorphism, will be called the standard cylinder object, and we denote it by B cross I. Okay. And from here, we can describe something. Okay. I mean, this is actually an individual, independent definition. Yeah, given f and g, I haven't really used f and g so far. Yeah, this is a cylinder object. And now I'm going to start talking about this given f and g. A left homotopy from f to g is h from b dash to x for some cylinder object b dash for b such that h composed with I0 is equal to f and h composed with I1 is equal to g. Okay, so from B to B plus B, there are two maps, nu1, nu2, the co-projections. So you get via this, and then from B prime to X. So this is like continuous deformation, right? You are putting a cylinder, you have got two different copies of B, and you are putting a cylinder object in between, and through that cylinder, we are describing homotopy. This is our standard notion of homotopy, but it's only the left version. We can also get a right version, and for that we use the path object. So the dual notion of right homotopy, homotopy is usually abbreviated as HTPY, uses path objects, and you will use the other functorial factorization or other type of factorization, yeah, acyclic cofibration followed by a fibration. So path object, the standard path object. So what is the standard path object in topology? It is the space of all continuous maps from the interval to our space. Okay, so standard path object for X is written x to the power I. X to the power I to denote the home, yeah, internal home. So that's why, but again, I has no meaning. There are no exponentials in the category of topological spaces. These are just for our understanding. So F left homotopic equivalent to G and F right homotopy equivalent to G. Okay, I'm not going to write down the definition, the dual definition. You should be able to figure it out on your own. And then what will be homotopy? So say that F is homotopic to G if, I mean written F is homotopic to G if F is both left homotopic and right homotopic.
So usual sense of homotopy, like, I mean, the right actually coincides with the path object definition.
The right is path object definition and the left is cylinder object definition. They both coincide in, yes, in most cases. Right, so I'm going to describe when. Okay, so if, let me give you one more definition. So say that F is a homotopy equivalence if there is some G, there is some H such that F composed with H is homotopy equivalent to identity on X and H composed with F is homotopy equivalent to identity on B. Yeah, so our standard definition of this, but we are using the two-sided version of homotopy equivalence over here. Okay, so when do we use left homotopy and right homotopy? These are not equivalence relations on their own. Yeah, left and right homotopy equivalences, they are not equivalences. So if B is a cofibrant object, then left homotopy is an equivalence relation on CBX. Okay, then you can write the dual version as well, yeah. If X is a fibrant object, then right homotopy is an equivalence relation. In particular, and its dual, yeah, and dual. Okay, so in particular, this is an equivalence relation on CCF. So on fibrant and cofibrant objects, two-sided homotopy is actually an equivalence relation because of just what I said. And in fact a congruence relation, because I only needed that the domain has to be cofibrant, the codomain has to be fibrant, but if I want to compose such morphisms, then I need that both domain and codomain are fibrant as well as cofibrant. And here you can show that it is a congruence. Congruence means it behaves well with respect to compositions. Okay, so now once you have a congruence, then what do? Quotient. So that is our definition. Okay, so now this is a deep theorem. I'm just going to write it as a statement. Yeah, you have to work a lot. So the localization W inverse C of C with respect to weak equivalences is equivalent to the quotient category CCF modulo homotopy equivalence. I told you that localization doesn't need additive, pre-additive, abelian, anything. You just need the willingness to invert certain maps and face its consequences. This is such a beautiful construction that it all happens smoothly around here. That you only take the category of fibrant, cofibrant objects and take quotient. So what will happen? Yeah, this localization is denoted, I will write C and loc. I don't want to give it some other name. Usually people use gamma and HOSI. And from this description, I think you will be pretty much convinced that what happens with HOSI. So HOSI XY is, yeah, if you take the same objects, then this is isomorphic to the morphisms from XCF, YCF, modulo the homotopy equivalence. Or if you want the middle version, then you can also take this, because you know that this is an equivalence relation. The homotopy equivalence classes of maps between the fibrant cofibrant replacements of the individual objects. Normally homotopy categories or localizations are massive, yeah, as I mentioned at the beginning of the lecture. So you have no control, but here you have very good control on the homotopy category because of this extra structure on the model category. You can actually see things. When you get an equivalence relation, isn't that beautiful thing? That it's a congruence, quotient out by congruence, and you get what you need. Right? So that's the beauty of this model structure. Well, another thing I want to say is that this particular diagram that I had here, yeah, this, let me call this diagram star at the top. These inclusions actually induce homotopy equivalences. I mean, that's these inclusions induce equivalences between the corresponding homotopy categories. Okay, so all inclusions in star induce, that is already included in the proof of this theorem. So all inclusions in star induce equivalence between respective homotopy categories. So by the way, I mean, let me refresh your memory that whenever there is some category D and a functor F such that all weak equivalences in C become isomorphisms in D, then there exists a unique functor from homotopy category to D. And this unique functor we will write as HOF, the homotopy F. This is the universal property of localization, yeah? But this localization happens to be a category, a locally small category. That's the important part. Perhaps this is too much of price to pay for such a simple outcome, but it is useful to do many things. Yeah, this whole idea. Okay, so do you have any questions before I proceed?
So I just need one clarification. So suppose if I take C to be the CHA, CH dot A, that is the chain complex.
Chain complex,
category,
yes,
chain
yeah.
complex category over any abelian
Uh-huh.
category, and I take W to be all the quasi-isomorphism.
Quasi-isomorphism.
Through this construction, do I get back the derived category?
Yes. But only in a special case. So, okay, if you want, I can give you the example right away. Okay, so one example of, so model structure on CH bigger equals 0A. Yeah, that's the restriction part I'm talking about. If I use the full chain category of chain complexes, then I can only get back the naive homotopy category, which is K dot. Whereas if I do work with only CH bigger equals 0, then I will get back D. Yeah, I think I'm saying it correct, because we had something. No, I think you have to also consider some projectives. So CH bigger equals 0 of proj A is actually the derived category of A. So this will help you to get the derived category, is equivalent to the derived category. Yeah, we wrote that. D bigger equals 0 of A. That is equivalent to K bigger equals 0 of this. So that should give you this. Okay, so what is the model structure over here? So the cofibrations, yeah, they are monomorphisms in each degree with projective co-kernel. Then the weak equivalences, these are quasi-isomorphisms. And the remaining thing, the fibrations, are epimorphisms in each non-zero degree. Well, I can also change it slightly. There is another model structure on this category where I choose cough to be COF to be monos in each degree, W to be quasi-isomorphisms, and FIB to be epis in each degree with injective kernel. Just dualize that. Yeah, and if you know something about extant Tor computation, then you use one of these two approaches. You either use the projective resolution of the domain or the injective resolution of the codomain. Yeah, it depends. So those come from these two different model structures actually. So this is the model structure on the category of chain complexes in non-negative degrees. Okay, then well, let me write now. Now I have started talking about this, so let me write something about model structure on. Okay, I should say Quillen model structure. This was given by Quillen. There is another one. So Quillen model structure on top. Yeah, so the category of topological spaces. Okay, so cofibrations are retracts of, just for the record, yeah, retracts of relative cell complexes. I will talk more about this when I describe cofibrantly generated model structures. Okay, so relative cell complexes I already explained, yeah, very loosely. Then W is homotopy equivalences. Obviously, that is what you want to invert, and fibrations are the so-called Serre fibrations. In the other model structure, other standard model structure on the category of topological spaces, you use Hurewicz fibrations and homotopy equivalences, and then appropriately cofibrations are determined. Yeah, it's enough to just tell you fibrations and weak equivalences or cofibrations and weak equivalences. I haven't really described what they are, like these are just names, but for the record, this is what is happening. And okay, on, so Quillen model structure on S sets, simplicial sets. Okay, so I think we have never talked about simplicial sets in the class. We should describe what they are. Yeah, so this is the category of contravariant functors on a relatively simple category delta op. Yeah, so this is objects of delta are natural numbers, and if you remember my rule in this class, in any foundational course, 0 is a natural number. Okay. So objects of delta are natural numbers and morphisms of delta are monotone maps. Now each monotone map is generated by a composition of, like a finite composition of sequences of some standard monotone maps. Yeah, the boundary and degeneracy maps or face maps, there are different names for this, and very beautiful combinatorics as well as category theory happens here in this category of simplicial sets. In fact, the category of simplicial sets is actually called the combinatorial model of topological spaces. So what happens is, for each delta functor from delta op set to sets is what? For each natural number you are given a set, and then there are some maps between those sets. So it's a family of sets x0, x1, x2 dot 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 indexed by natural numbers together with certain maps between them. Okay, so x0 can be thought of as points x1 can be thought of as one simplices, x2 can be thought of as two simplices, and so on and so forth. So basically, there is a natural way of constructing a topological space by simply gluing these simplices together and with respect to appropriate quotient topology. So, well, before describing the model structure, let me tell you that from the category of simplicial sets to the category of topological spaces, there is a functor which is called the geometric realization functor. In the other direction also, there is this singular simplicial complex set. This is the singular complex functor. Okay, and the main point here is that there is an adjunction. Okay, this adjunction is quite important. So this adjunction, so there is an adjunction. I obviously don't have enough time to talk about the details of this adjunction, is a Quillen adjunction. Okay, so what does that mean? I.e., okay, so let me define what is a Quillen adjunction. If the left adjoint, i.e. the left adjoint preserves this is happening quite at the wrong time. I haven't described the model structure yet, but the left adjoint preserves cofibrations and acyclic cofibrations. It's an adjunction with these two properties. Okay, I mean, if you want a functor to be a functor between appropriately structured categories, then it has to preserve some structure. But see, it's not asking for everything, that cofibrations, fibrations, weak equivalences, everything is preserved. That's not the point. Just these two are preserved. It's one half of the definition. Okay. So this is a Quillen adjunction, and any such Quillen adjunction, okay, so this is perhaps any Quillen adjunction induces an equivalence between homotopy categories. Very strong property. Okay, so i.e. what's happening here, that is that's the singular simplicial complex, simplicial set. If you know what singular complex, the chain complex, how we constructed, yeah, so I mean, we never discussed it, but it's same thing, two simplicial sets. I mean, the technical machinery is hard. You have to talk about the co-simplicial object in some appropriate category, so I'm not going to do that. My main point is that the category of the homotopy category of topological spaces is the same as the homotopy, is equivalent to the homotopy category of simplicial sets. There is something called, yeah, something very deep called the homotopy hypothesis. So it says, yeah, it's a hypothesis, yeah, it's not a theorem or anything. It's a hypothesis. It states that topological spaces are nothing but infinity groupoids. And this is the mini version of that. Infinity groupoids are entirely given, like groupoids, you understand? Yeah, the groupoids means every morphism is an isomorphism. Then you have morphisms between morphisms and more like homotopy equivalence, yeah. And in topological spaces also you have the notion of points, then you have paths, and there are paths between paths, namely maps from I square. Yeah, the homotopy between paths. Then homotopy between homotopy of paths, and this process never ends. So that's why it's called homotopy infinity category. So that homotopy hypothesis claims that infinity groupoids are just topological spaces, and this is the you can say the one-dimensional version of that. That even though topological spaces can be really bad, think about spectral spaces, Zariski spectrum, Ziegler spectrum, that kind of things. They are not even Hausdorff. Then homotopy is not really a way to study those spaces. But you don't really need to worry. This adjunction will solve all the problems. You can always, I mean, what it says that you can replace a topological space by its fibrant cofibrant replacement. And that is a simplicial complex. It's a simplicial set. Yeah, it's a very nice topological space which can be combinatorially described. Simplicial sets have combinatorial description. So that's why this Quillen adjunction is important. Any questions? Okay, I just want to cover one more thing. I know this is a long lecture, but I will give you a very simple kind of description. Without that, really you can't complete the discussion on model categories. I want to discuss something called small object argument. Ultimately, I will describe that, and then I will describe how to construct model categories using this. So small object argument is the ultimate goal. I am not going to start right away with it. Okay. So recall some directed colimits. Directed colimits, you understand? You remember that directed set is a partially ordered set where any two elements have got a common upper bound. And if the shape of a colimit is directed set, then you say it's a directed colimit. Now, ordinals are directed sets. Okay, if you don't know what ordinals are, just think about 0, 1, 2 up to n. Yeah, the entire collection, omega, just think about omega. Omega is a directed set. Yes, so any two elements have a maximum. So therefore that maximum will act as a common upper bound. Okay. So if ordinals are directed sets, then we should be able to take co-limits of an appropriate shape. Okay. So if C is a co-complete category, and F from an ordinal to C is a co-limit preserving functor, then define the transfinite composition I mean, maybe I should use word X. Yeah, it will give you more sense, a better sense of this. Transfinite composition of the system X is the co-limit of X. Okay, maybe I haven't really said anything, but see what's happening. Like suppose X is given like this. So x0, x1, x2, and then there will be some maps f0, f1, f2, and so on. Then ultimately, there will be x omega. The limit of all finite ordinals is omega. But what is omega? Because it's a co-limit preserving thing, so x omega will be the co-limit of n less than omega of xn. But the process doesn't stop here. Yeah, you again have x omega plus 1 and you continue, then you will have x omega plus omega and so on and so forth until you reach a particular ordinal. Yeah, that ordinal is the shape alpha. So as long as this entries, the indices, the subscripts of x are less than alpha, you continue doing this. Then the ultimate co-limit is the transfinite composition. Now obviously co-limits are not unique. However, co-limits are unique up to unique isomorphism. So therefore the transfinite composition, is the map, I'm making a mistake, is the map from x0 to co-limit of x. Yeah. So whatever happens ultimately, that whole thing is called the transfinite composition. Very beautiful concept. Yeah, I really like it because you normally think of composition as a binary operation. But here you can talk about infinitary compositions. Okay. You understand this? Transfinite compositions can be defined in a category with co-limits. Okay, beautiful. Now, given, I'm going to sweep lot of things under the carpet. So given a set I of morphisms of a model category C such that we can define various classes of morphisms. So I inch like are the morphisms having the right lifting property with respect to all morphisms in I. Then I proj can be defined to be morphisms having the left lifting property with respect to all morphisms in I. Then I cough is defined to be I inch proj. Are you understanding what I am doing? Okay, let me say something in the form of a diagram. See, if I have a commutative diagram like this, then this particular morphism will belong to, like if I vary this over I, then this particular morphism will belong to I inch. If there is a lifting, okay? If this belongs to I, then by starting with this, then I will get this. So the implication is in this direction. If I now understand I inch, then I can do this reverse process. Right? So I can come back. If I know that this morphism is in I inch, and then I want to talk about all the maps which have left lifting property with respect to I inch, then I will say that this map belongs to I cough. So this is the second stage. Then you can imagine what I fib would be. I fib would be I proj inch, right? But the story doesn't end here. Yeah, we have to talk about something slightly different. So I cell is a subcollection, we don't necessarily need all of them, of I cofibrations such that every morphism in I cell is a transfinite composition of pushouts of morphisms of elements of I. So I cell, the elements of I cell are called relative I cell complexes. So what happens, like consider this push out diagram. If you have something in I and now you consider this push out. So this particular morphism is in I cell. And if you stack such things one after another, then you will get a transfinite composition of morphisms in I cell. Yeah, but you are stacking it vertically, one below another. So the morphism, the sequence of morphisms that we wrote above, x0 to x1, x1 to x2, they are all such pushouts of morphisms in I cell. Right? So this is the idea. So in category of topological spaces, this you have to know. Yes, in category of topological spaces, we choose I. Let me check the notation. Yes, choose I to be the set of, the inclusion of Sn minus 1 into the disk Dn, where n is in n. Okay, so this is what we need. S minus 1 is empty here, by the way. Yeah, if you worry about that. S minus 1 into D0. So then you understand why this is the same concept which captures relative cell complexes, the topological, because you are simply starting with some topological space. This starting point x0, that is not within our control, but what we are doing with it, that's within our control. Okay, so just let me say what this last thing is. Small object argument I will state and then we will end. So the small object argument theorem it says that provided a set I of morphisms of C such that some technical condition is satisfied, the domains of maps in I are small relative to I cell. I am not going to describe what this is, but some finiteness condition you can think of, or smallness condition. There is a weak factorization system, namely I cell ING, and a functorial factorization gamma delta corresponding to it. So what we do is we construct a weak factorization system only starting with a collection of maps, which are nice. Yeah, Sn minus 1 to Dn, those are nice. So we can construct a weak factorization system, and if you want to construct a model category, then you need to start with two sets of morphisms, I and J, and then you will construct two factorization systems, weak factorization systems simultaneously, and that is called a cofibrantly generated model category. So this transfinite composition is a tool that is very useful. That's extremely useful, and I believe that the concept of transfinite compositions is far more interesting. And most of the model structures that we have seen, they are all cofibrantly generated. Okay, so this I is called the set of generating acyclic cofibrations, I think, or set of generating cofibrations. Yes, and J is the set of all trivial cofibrations, generating trivial cofibrations, and then you generate a model structure out of this. Okay, let's end it here. If you are interested, then please study model categories. You can do very good abstract homotopy theory in settings that you never imagined with this.